Okay. Hi everyone, I'll be talking about separating k-median from the supplier version. Okay, this is joint work with Euiwoong, my advisors. And the k-median problem has been defined so many times in this, but since we have these two versions, I'd like to just define it so that we're all on the same page. Okay, k-median is just you're given a set of points, you want to open k centers so that each point goes to its nearest center, and then you sum up all these distances, and that's your cost function which you want to optimize. Okay. Yeah, so and in this talk we'll be working with the metric spaces. We won't be looking at the Euclidean version. And the supplier version is, of course, very similar to the K supplier. It's like you have two sets, L and F. L is the set of clients and F is the set of facilities. So you need to open K facilities so that each client goes to the nearest facility, and then you sum up all these distances, and that's your new objective function. So in some sense, this is a harder problem because, okay, if you can solve this problem, then you can solve the non-supplier version. Just you can set both the sets to be the same set because you can open centers anywhere to non-supplier. Okay, so why are we interested in this? Before that, let's look at what's the current state of the art for k-median. Again, many of you might know this, but quickly, okay, the first constant factor approximation was 6 2/3 approximation in the late 90s by Charikar et al. And then there was this. So many works in the last 2 decades. They've been using local search, 5-point rounding, primal dual methods, a lot of methods. And the current approximation is somewhere around 2.6. And one thing is to note is that this works for the supplier version as well. We will come back to this. And what about the hardness of approximation? So the best known hardness of approximation for k-median is this 1.73 for the supplier version, and it's like 1.36 for this vanilla version of k-median. So that's, we can already see that there's some gap between these two versions in the sense that the hardness is not the same. And okay, more recently, people have also been interested in this parameterized algorithms for k-median. Okay, in some sense, we ask the question: what if you allow the algorithms that run in time some function of k times poly n? So it's like could be 2 to the k times poly n, something like that. It's kind of reasonable if k is small. That's the first motivation. And the second motivation for studying this is that, okay, it might be some kind of meaningful prediction for the polynomial density, because there we're not able to narrow down the approximations so much. There's quite a gap between the best known lower bound of 1.7 and the 2.6 algorithm. Okay, so the question is, okay, can you do better if given parameterized running time? And indeed, it turns out that you can get a 1.73 approximation, and this is optimal for the supplier version. This was shown in very recently, 2019, by Anand, Gupta, Kumar, Lee, and D. And one common feature.
The function of k? Is it
so the function of k is something like k to the k, I think. Yeah. And all the algorithms for k-median in the last 2 decades, one common feature of them is that they've all worked for the supplier version also, including this parameterized algorithm that I listed here. And one partial reason for this, at least, is that in polynomial time algorithms, the techniques have been based on facility location, and then facility location all gives you this natural separation of the input into facilities and points. So whenever you have some alpha approximation using facility location, it transfers to an alpha approximation for the supplier version also. But there's a gap in the best known hardness. Even in the parameterized setting, the best known hardness are 1.36 and 1.73 for the non-supplier and the supplier. So, okay, this brings us to the main topic of the talk, or what is a very natural question. Is k-median easier than the supplier version? Is it easy to approximate k-median as compared to the supplier version? Well, okay, of course, for k-center, the same question has been asked long ago, and it's been settled that 2 and 3 are the right approximation factors. So there is a strict separation in the k-center world. So it's very natural to ask if the same thing is happened for k-median, and no distinction is known so far. And so our result tries to make the first progress towards giving such a distinction. So let's see what our results are and how they fit in the context of the existing work. So the first result will be a parameterized algorithm. Like I told you, there's a 1.73 approximation that works for the supplier version. It also translates to 1.73 for the regular k-median, but the hardness are 1.73 and 1.36. So our first result is a 1.54 approximation for the k-median, the non-supplier version. So in some sense, it goes below the 1.73 hardness for the supplier version, which means that these two versions, at least in the parameterized setting, they are different. Their approximability is actually different. And the second result is an improved polynomial time hardness. So the hardness is 1.73 and 1.36, even the polynomial type regime. We improve the hardness to 1.4 for the non-supplier. So those two are our results. Let me restate them because there's some nice structure to these results, which you can see. So these are our results. But okay, why did I put these expressions here? Like one thing, if you notice, is that these expressions almost look the same with the min and max switched. So okay, this is min over some probability p and max over some integer d of this expression, and then this is almost the same thing with max and min. But okay, there's some difference in the sense that okay, you see a d here and you see a d minus 1 here. So if you replace this d minus 1 by d, in fact, these two expressions are exactly the same. And one more thing is that the min max and max min of these expressions is actually the exact same. So the 1.54. So in some sense, if you could turn, let's say, d minus 1 to d magically, then these two numbers are exactly the same. So, okay, so that's one nice feature of the algorithm and hardness, which look almost the same. So in this talk, my goal will be to just convey to you the algorithm and completely convince you that the algorithm actually does get you something like a 1.54 approximation. The algorithm is quite simple, so I hope I can succeed in doing that.
And before you
Yes.
further, so the hardness is for poly.
Yes.
And the
So the hardness is for polytime and the algorithm is for parameterized algorithm. So both are the weaker counterparts in some sense. Yes.
But, you know, even if I manage to change the d minus 1 to a d,
Yes.
there would be hardness and approximation, but for different problems.
Yes. Yes. For different problems.
Mhm.
Yes. Yeah. So it won't settle anything, but yes. But there's some nice similarity at this point. Okay. So first, let's see how to get this 1 plus 2 over e parameterized approximation for the supplier version. This was already known by the algorithm of Cohen, Gupta, Kumar, Lee, and Lee, but I'll describe a slightly different algorithm which essentially has the same flavor. Okay. So first, okay, just reminding what's the problem. We have the steps L and F, and we need to select K centers from F, and the clients in L pay their cost. So the first concept you need is that of core sets. Okay, so many of us are familiar with core sets, but in this talk, I won't need them too much. I just need some very basic thing, but let's see. Okay, an epsilon k core set is a set of weighted clients, so that if you pick any k centers, the cost of assigning the points to the centers is the same up to 1 plus epsilon factor after replacing the client set by this weighted clients. And there is an epsilon k core set which is of size k log n over epsilon square. This is known from a long time. And basically for this problem, what we can pretend now is that the set of clients is of size at most k log n. Okay, they're going to be weighted clients. But okay, let's even assume that these clients are unweighted for this talk because all the things are just going to directly translate to the weighted case. There's nothing about it. Okay. So let's see how to get the 1 plus 2 approximation. So first you look at the optimal clustering. So it has some optimal centers, F1 star, F2 star, Fk star. And okay, what we're going to do is guess the leaders from each cluster. The leaders are basically the closest client in each cluster. So L1 is the closest client in the first optimal cluster, which is closest to the optimal center, and so on, L2, Lk. So you're going to guess these things. The next thing you'll guess the distances of the leader to the closest center. So you're going to guess these distances R1, R2, and R. First, let me convince you that okay, you can do these things in parameterized time. That's not too difficult to see. Okay, you only have k log n clients now, so the number of choices for these k leaders are going to be something like k log n choose k, which is something like k to the k. And for the distances, there's some intricacies involved, but it's really technical in the sense that you can't guess the distances exactly, but you're going to guess the distances to the closest power of 1 plus epsilon. And you can assume that the distances are polynomially bound. So then there are only log n choices for each distance. And so you'll be able to guess these distances R1, R2, Rk. All these guesses can be made in parameterized random time. For this talk, again, let me assume that these distances are even exact because that difference is not very important. Okay. So now let's see how to proceed further. We are now going to get these sets Fi, which are at distance like Ri from the leaders Li. So you get these sets F1, F2, F3, Fk. In some sense, these are the candidate sets from which we want to pick the optimal center. We want to pick one center from each set Fi. And we know for sure that the optimal center will be in this set. So the F1 star is going to be in F1, F2 star is going to be in F2.
Those may be overlapping, right?
They may be overlapping, but you can just make some copies and make them disjoint. So that's not a big issue. You know that there's one way to open like only K anything so that so if they overlap, you can just make copies of them. For K million, we don't care about it. If you open two centers twice, then it is good. Okay. So once we have these sets F1, F2, Fk, we write this LP relaxation. Okay, what's the LP relaxation? So the variables are going to be this for each client C, there's going to be this variables XCJ, which basically indicates if C is going to be assigned to J. And there are for every center J, there is a YJ, which basically indicates is J open. Okay, so it's a very natural LP relaxation. You might have already seen some very similar variant of this. Okay, the first, you're trying to minimize the connection cost. And the second constraint is saying, okay, you can only assign C to some center J if it's open. The third constraint is saying that every point must be assigned to some center. And the fourth constraint is saying every Fi we should have exactly one center open. So this is the only thing that the guessing helped us achieve so far. In the normal K median, you would have written the constraint that the total number of centers open is K, but now we are going to insist that from every Fi we open exactly one. Okay. So is the relaxation clear? Yeah, feel free to stop me at any time if you have any questions. Okay. So once we have this LP relaxation, okay, what's the rounding algorithm? It's super simple. The LP relaxation gives you these numbers, which are for each facility, the probability with which it is open. You're going to choose exactly one center from each Fi. So from F1, you're going to choose one center. And how you're going to choose it is the probability will be proportional to these numbers, YF. So in the first F1, you're going to choose this with probability 0.5, this with 0.2, this with 0.2, and this with 0.2. Not independently, but you're going to choose exactly one center with each F1. That's the rounding rule. So let's see why this is a 1 plus 2 over approximation. Okay, let's define a few things. These will be needed as we proceed. So for every client C, let me define this set NC. NC is basically the set of facilities J, which I send flow to, or I'm connected to with non-zero probability in the LP system. And the LP of C is basically the connection cost of client C in the LP, the fractional connection cost. And I can also define opt of C, the connection cost of C in the optimal solution itself. Okay, so these three things we can define. Okay. So let's first ask this question. Let's fix any client C. And now let's ask the probability. What's the probability that no center of NC is actually open? Okay. That is at most this quantity. If you look at any center Yj, the probability that it's open is like Yj. So the probability that it's closed is 1 minus Yj. And the probability that none of these things are open is at most the product of all these 1 minus Yj's. Okay, if they were in the same cluster, it's even going to be better for this client. So if all of these clients were in the same Fi, then this probability is going to be even smaller, the probability that none of these things are open. But if they're in different clusters, then essentially they're independent. So the probability that none of these things is open is at most the product of the 1 minus Yj's. And okay, this is some standard analysis. You know that the Yj is at most at least the XCJ value. So this whole thing is at most e to the minus XCJ summed over all j. So that's at most 1 over e because the sum of all the XCJs is. So what this is saying is that if I'm a client, then look at my neighborhood in the LP solution the probability that none of those things are open is at most 1 over. It seems like a good thing. Okay, so what do I do if none of my neighbors in the LP solution is open? Then what I'm going to do is this. I'm going to go. Okay, so I know I'm connected to some optimal center. And remember that that optimal center is in some Fi. I don't know which Fi. It's in some Fi. But there is going to be some other center that's open in Fi for sure, because from every Fi we're opening this one center. So that means I can now assign this client to that Fi. And okay, how long do I have to travel to reach Fi? So the distance from C to Fi is at most, by the triangle inequality, these 3 hops, 1, 2, 3. And then the first hop is exactly how much you pay in your optimal solution. And the second and third hops are actually also good. And that is because how we define these leaders. Leaders are basically the closest clients to the optimal center. So this Ri is going to be less than this, and this distance is also Ri. So all these 3 distances are in fact at most the optimal distance. So that gives you a connection cost of 3 times opt when no facility in your LP neighborhood is open. Okay. So basically we have these 2 cases with 1 minus 1 over E probability. We are going to go to the closest open center in NC. And if no center in my neighborhood NC is open, I'm going to go, we take these 3 hops and go like pay a cost of 3 opt. Okay, so then there's one technical thing which I'll just say, that if some center in NC is open, then the expected cost is actually at most LP. This is slightly non-trivial, but it's very easy. It's easy to see. So then, okay, what happens? So your approximation ratio is like 1 minus 1 over E times LP plus 1 over E times opt. So that gives you a 1 plus 2 over E. Okay. So now let's see how to do better for vanilla K-median. Like how can we exploit something more? So if you look at this picture again, let's say I'm allowed to open centers anywhere. So I had to travel, if none of the centers in my neighborhood was open, I had to go like 3 hops. So I had to go from C to my optimal center to the leader, then to the center that's actually open. But let's say there was a center that's open at the leader itself. And that's good. Then I don't have to travel 3 hops, but I can only travel 2 hops. So I'm only going to pay 2. So if I can open centers anywhere, it seems like, okay, opening the leaders is a good idea. So if I open all the leaders, I'm going to get a 2 approximation. That's it. But okay, opening all leaders gives only a 2 approximation, and we want to like beat 1.7. So what do? So what's the most natural thing that comes to our mind when we look at this is, let's do both. So choose some threshold P, which is going to be some parameter. And then for each set, either I'm going to choose the leader Li, or I'm going to do what the previous algorithm is doing. So with probability P, I'm going to open the leader. And with probability 1 minus P, I'm going to open exactly one center F from Fi with the probabilities Phi. And basically, the rest of the analysis just says that our result is just that this simple algorithm gives the 1 point. Okay. So, okay, we're going to analyze this algorithm. But first, let's analyze this for a special case. It will be easier. So, I'm just going to assume that the metric is an unweighted graph. So, it's an unweighted bipartite graph where each edge length is 1. And we'll also assume that in optimal solution, every client is connected to its neighbor. So everyone plays only a distance, a cost of 1. So the total cost is exactly n, the number of clients. So these are the 2 assumptions that we're making. Okay, third assumption is that every client has the same degree d. This is not so important. And yeah, so basically each client is now getting assigned to a distribution on its neighbors. And let's see how this algorithm does in this special case. Yeah, before we go to the analysis, let's see why intuitively this should be a good algorithm. Okay, so there are 2 cases. First of all, the neighbors of client C can be distributed, really distributed across all these Fi. Maybe it has neighbors in so many Fi, at least 100 Fis, let's say. In this case, the algorithm should be good because in each of these Fi, with probability P, we open the leader Li. And even if one of these leaders is open, let's say L1 is open, then you're going to get a cost of at most 2. Similarly, if L2 is open, you're going to get a cost of at most 2. So even if one of these leaders is open, you're done. So even with a really small probability of opening leaders, you can actually make sure that the worst case for this client C is in fact not 3, but it's 2. So the worst case is getting improved from 3 to 2. So that seems like a good thing. Because yeah, if we reduce 3 to 2, we are going to beat 1 plus 2 for sure. Okay, what's the other case? Yeah, basically this is saying what I just said. The other case is when you have neighbors only in a few clusters. This seems like a good thing again because this client is almost like integral according to the LP. The LP is just saying you're only selling flow to these 100 FIs. What should happen then? There should be some FI to which your total flow, the total LP mass that you send, should be at least 1 over 1 because you have to get matched. But this means that with probability 1 over 100, some neighbor of C is actually open in this. Because remember that in this, each Fi we open exactly one center proportional to its probability. So this is also a good case. So we have this win-win case, which is basically the motivation of why we are able to beat 1 plus 2. Okay, so let's analyze this fully and see why we get the number that we get. Okay, what's the probability that no neighbor of C is open? Okay, so that's what we want to first analyze. So for each Fi, let's define the flow, mu I. That's the sum of LP values of C inside Fi. So when does C have a neighbor in Fi that's open? It's open only if Li is not big, so the leader should not be big. And given that some neighbor of it should be big, so that happens with probability mu I. So the probability that some neighbor in Fi for C is open is exactly equal to 1 minus P times mu I. So the probability that no neighbor of C in Fi is open is this 1 minus P times mu I. Okay, this is the bad case in some sense. If you don't have any neighbor, you're going to pay at least 2. And then, okay, even worse things could happen. Maybe no neighbor of C is open and no leader is also open. So maybe Fi, no neighbor of C in Fi is open and the leader Li is also not open. In this case, okay, you should think that you pay 3 because you can't go 1 hop or 2 hop, you need to go 3 hops. And that happens with this probability. Okay, 1 minus P comes because you don't want to open the leader and 1 minus mu I because you don't want to open anybody who's adjacent. Okay, so let's put it together. With probability at most this, the product over all I, 1 minus P times mu I, you pay a cost more than 1. So you pay at least 2. And with probability at most this, you pay a cost more than 2, which is you pay 3. So what is the expected cost bounded by? The expected cost can then be bounded by, okay, 1 is your baseline cost. This is the probability with which you pay something more than 1. And this is the probability with which something you pay more than 2. So it should just be the sum of these 3 terms. And it turns out that the worst case is actually when the flows are all regular. So it's like each flow is the same, mu i's are all 1 over d, and that gives you this expression. Yeah, and then if you set P to be some value, you're going to get upper bound of 1. Okay, so let's see how much time I have. Like 5 minutes. Okay, let me tell you some intuition about how we deal with the general case. Well, it's a little more complicated than these regular cases. But what we try to show is in some ways that all distances are the same. But now we have to be a little more careful. Maybe you're connected to some center with non-zero probability in the LP solution, but maybe that center is actually quite far off, right? If that center is far off, even if its leader is open, maybe I shouldn't go there because the cost is actually going to be quite a lot. So now I cannot go to every leader. Maybe I can only go to some of the leaders which are open. So basically, I'm only going to go to the close enough leaders. Otherwise, I'm going to settle for maybe 3 times my smallest distance. That's like some idea for how we obtain this general case. So when the distances are irregular, actually, this turns out that you can actually write this as an LP. The worst case for a client can be written as an LP in terms of the distances, and you can show that the regular case, in some sense, is the worst case for that LP. And then, okay, we can optimize the flows, we need to optimize this, but that's just some technical calculation. It turns out that this regular case is always the worst instances. And okay, what are the implications and conclusion? Okay, we showed that there is a strict separation between the supplier version and the non-supplier version of k-median, at least in the parameterized world. And okay, this is a belief, we can match parameterized time with only poly time. Okay, everybody doesn't believe this. I know something doesn't believe it. But if that's true, then okay, the right number for this k-median, the regular version, is going to be between 1.4 and 1.5, something like that. Okay, open questions, of course. Can you get polynomial time algorithms for k-median, which will significantly outperform the supplier version? So that's one question. And then the second question is, can you close the gap between the upper and lower bounds? And also, like Anupam said, like, can you make sure that the lower bound works for the parameterized setting, or the upper bound actually works for polynomial times? So, yeah, that's it.
We had time for a few quick questions.
Is there a problem with the case center like W1R? You need to supply this.
Case center, yeah, I think it should definitely be hard.
So 1 + 1 by E hardness goes to
1 + 1 by, yeah, I think so. I think it should be. No, for case center, it's case center is going to be 2.
center.
Yeah. So the 1 + 1 over E hardness is going to be 2 for sure, even in the parameters. But we don't know whether where it is would be 1 + 1 over E and 1 + 2 over E.
But does your work also apply separation for k-means when you use square distances instead of?
Yeah, we didn't think about it formally, but probably should. That's the case. Yeah. Normally, we triangle inequalities. Something should transfer. Yeah.
The hardness goes. Could you show the expression once again? I want to see where the d-1 versus d thing is appearing.
For the hardness, you mean? Or
No, in this sort of calculation, where did the d-1 versus
In analysis?
the PID analysis?
Yeah, I think in the analysis for the algorithm, there's only d. There's no d-1.
Right.
Yeah, where it show up as D and not D1.
Yeah, exactly.
Yeah, this is the expression for the algorithm.
Or because the worst case.
Yeah.
So yeah, this is the. Yeah, I guess the guess is that the algorithm should be the one to improve rather than the hardness. That might be the easier thing to do. I don't know. It should be possible, I guess, but yeah, I don't know how to do it now. Probably, actually, I think we were also thinking that the LP itself, the integrality gap might actually be close to something like this. Yeah, there might be some way to show that. Like, so the hardness that we prove the polynomial time setting, that's there is a d-1 versus d question. But if one wants to just prove maybe some kind of integrality gap, maybe one can remove that d-1 versus d at least in the hardness.
Okay, good. Thanks, speaker again.